Alright, so today we're going to be doing lesson 6.1, which is the first lesson of our exponential functions and exponential growth and decay section. So let's get started on some vocabulary. So the first vocabulary we have here is asymptote. So an asymptote is an imaginary line, which is where your graph approaches. Every single exponential function has one of these. Even if it's flipped upside down, it's going to have one on the top. And an asymptote can either be vertical, it can be horizontal. It can also be diagonal. We won't get into diagonal asymptotes too much in this class, but they do exist in different types of questions and whatnot, types of graphs. But not so much in this lesson. This is a horizontal asymptote. Okay. As you guys can see, this is horizontal. And it is a characteristic that all exponential functions have. And the end behavior is how the ends of the graph behave. So basically, as we go to x in the negative direction, as we go to x in the positive direction, what is the function doing? Is it stopping at one point? Is it going to negative infinity? Is it going to positive infinity? That is going to be things that we need to figure out about our graph. Now, asymptotes are going to be a really key thing in this lesson. You're going to have to be able to identify them, and they're really going to help us sketch graphs. So they're really important as a concept in exponential functions. So this is what we would call standard form of an exponential function. Now, in Algebra 1, you probably saw this. F of x is equal to a times b to the x, and you probably saw this as your standard form. Does anybody think that looks familiar to them? So that's what you would have learned in Algebra 1. So in Algebra 2, we kind of add a little more depth to it, and we talk about the horizontal and vertical shifts, as well as the reflections, compressions, and stretches of the graph. So there's a few different things I want to talk about in terms of this equation and what's important. So this number on the outside, a, affects if it's stretched, compressed, or reflected. If it's negative, it's going to be reflected. If its value is between 0 and 1, it's going to be compressed. And if it's greater than 1, it's going to be stretched. So if you remember back to our unit on sequences and series, geometric sequences are actually models of exponential functions. So the a is actually similar to your first term or your initial value. So if you do want to write that in, you can. Initial value or first term. It's not exactly a first term, but it's basically your starting point, your initial value that you start with when we're talking about it in a real life context. So it's similar to your A1, which you guys have been learning about. And your B, anybody have an idea on what B is similar to? Your common, common ratio or rate. So that's how it corresponds to a geometric sequence, okay? It has the similar properties to that, only we're looking at it in terms of a function instead. Now, the horizontal shift, you can indicate a horizontal shift because it's going to be subtracted or added from x. Now, if it's subtracted, it's going to the right. If it's added, it's going to the left. So it's always the opposite sign, okay? And then a vertical shift, oh, I forgot to mention. If your b value is greater than 1, that means you have exponential growth. This function's going up. And if it's between 0 and 1, like a fraction, it's going to be decay, going down. And the vertical shift, this affects your vertical shift, okay? This is telling if you're going to go up x amount of units or down x amount of units. If it's minus, it's down. If it's positive, it's up. And it's also important because y equals k is also your horizontal asymptote. So you can always find the horizontal asymptote by finding k. Now, what if your function doesn't have a plus k at the end? What would your horizontal asymptote be? 0. It would be y equals 0. It would be the y equals 0 is actually the same thing as the x-axis, by the way. So it would be y equals 0. So that's some important things to note about the setup of an exponential function. So this is like the most basic form of it that you might see, and this is like the more complex version, understanding the shifts and whatnot. So like I said, this is probably what you saw in Algebra 1. Algebra 2, we kind of go in more depth regarding these types of functions. Alright, so the first one we're going to talk about is exponential growth. And we're looking at this from the example of this function y equals 2 to the x. Okay? So in this case, y equals 2 to the x, if you think about the standard form, this one has an a value of 1, because there's nothing on the outside, has a k value of 0, and an h value of 0. Because this is very simple. Okay? So, as the x values increase, the y values decrease. Now I mentioned that y equals k is your horizontal asymptote. In this case, what is your k value? So the k is what's added at the end. So what's added at the end here? 0, nothing, yeah, so it's just 0. So that's your asymptote. So your asymptote's this right here, y equals 0, which is the x-axis. And you guys see how that fits with the graph itself? So in terms of an asymptote and an exponential graph, your graph approaches that asymptote, but it never actually does what? Never crosses it, never touches it. And that's because with exponential functions, you put something to a power and it never will be 0. There's nothing you can put, no exponent power you can put on any number that will ever get you 0. So you can take, what's 2 to the 0 power? 1. And if you do a fractional exponent like 1/2, that's going to be 1/4. You're always going to either get a decimal or you're going to get a number that isn't 0. Okay? It can't be 0, that's why. So that's kind of why we have these asymptotes, for that reason. You can't make it something that has an exponent equal to 0. So exponential decay is the exact opposite of that. Your function is starting up and going down. Okay, and that happens when your b value, this is your b value by the way, it's the one that has the exponent, is between 0 and 1, which 1/2 is. As the x values increase, the y values decrease. The y values actually go to 0, right? Your asymptote here is also y equals k, which is 0. So they approach that asymptote, but they never actually touch it. So you can pick really, really, really small negative values for your exponent, and it will always give you a positive, very small value for your output. And that's because that's a characteristic of exponential functions. So now we're going to talk about some transformations that can happen to an exponential function. We're going to talk about some basic transformations. So when I first looked at this, this chart, like when we were coming up with examples here, I want to make sure this is clear to you because it wasn't clear to me at first. This right here is the original function, which is y to the 2x. I'm sorry, y equals 2 to the x. So that's the original function, and we're going to be manipulating it. So we're going to try to regraph it with a manipulation. So in this case, what did we do here? We changed the a value. The a value was 1, but now the a value is 2, right? So when the a value is 2, that's actually a vertical stretch. It's stretching your graph vertically when your a value is bigger than 1. So here's how you actually find the new graph without actually doing a table. You take a few points on this graph, so just plot a few of them. I should probably do it in blue to not confuse you. So I plot a few points. So pick ones that fall nicely on the coordinate plane. Don't pick ones that are like decimals, unless you have to, but I prefer not to. And now we're going to apply this vertical stretch, okay? Vertical stretch. So if it's a vertical stretch, it's going to be affecting its y values, right? And it's going to be multiplying them by what? 2. So we're going to take our y values and multiply them by 2. So what's 1 times 2? 2. This is moving up to 2. So I multiplied it by 2. And now again, we're going to take our next point. Take the y value and multiply it by 2. So what's 2 times 2? 4. So this one's moved up to 4. Excuse me. And this one right here is at 4. It would go up to 8, but as you can see, that doesn't fit on the graph, so we're just going to leave that point out. But we do have a few points, right? So we can now sketch this again. And your sketch doesn't have to be perfect because it's just a sketch, okay? It's going to look something like this. Now, keep in mind, I can't draw it perfectly, but this actually doesn't really touch the x-axis, okay? It doesn't actually touch it. It's hard to draw, you know what I mean? So it doesn't actually touch that axis. It still has the same horizontal asymptote. the asymptote hasn't changed, it's just stretched. So basically what this did to the function is it makes it go up faster. It stretches it this way. So any questions about a stretch? Now if you're more into like a concrete approach to this instead of like a visual or conceptual approach, you can also always make a table, x and y, and you can just pick a few x values to plug in, so like 0 and 1, plug those into this function. Well, 2 to the 0 power is what? 1. 1 times 2 is 2. And then what's 2 to the first power? Good. 2 times 2 is 4. So you got 2 points that way you could have graphed as well. So you can also do a table approach if that's what you feel more comfortable with. So any questions on this first part? Alright, let's move on to the next. So on this one, our a value is actually less than 1, right? So we learned that if the a value is less than 1, this is a compression, okay? This is a vertical compression, meaning it's smashing it this way, vertical compression. So, same procedure as before. We have our original function, which is already graphed, which is y equals 2 to the x. And we're going to be taking the y values, but instead of multiplying them by 2, we're going to multiply them by what?
0.5.
Good, 0.5, which is the same thing as dividing them by 2. So we're going to take each of those x values, or y values, and multiply them by 0.5, also known as dividing by 2. So what's 1 divided by 2? 0.5, so that one falls right here. And what is 2 divided by 2?
1.
Good. And what is 4 divided by 2? 2. Good, so now we graph it. It is so much harder to graph it on here than by like hand. I don't know why. Because I can usually write on here pretty well, but there we go. So it doesn't actually touch the x-axis, but if yours does look like it does, that's okay. It's almost impossible to draw it to not look like it, as long as you know that. So as you can see, this was a vertical compression. See how it kind of compressed it down, your graph? So now your graph is going up slower, right? It's compressed vertically. And like I said, a table would also work here. If you prefer tables, you can do, say like you plugged in 1 and 2 into the function. You could compute these and you would get 1, 1, and you would get 2, 2. So, like I said, if you prefer a table, that's fine. So, moving on to the next one. We'll start by plotting some points on this one, just picking them out. Usually you want to pick ones that are nice points. And anybody have an idea of what this new graph is what's gonna happen compared to the old one? Flip. It's a reflection, right? Over which axis? The x-axis. Yep, it's gonna flip this way. So how we can actually compute this, you can draw it via reflection knowing the properties, but this value is really a -1, right? So you're going to take your y coordinates and multiply them by your -1, your a value. So what's 1 times -1? -1. What's 2 times -1? -2. And what's 4 times -1? -4. So as you can see, it's just going to look like this. It's going to be a reflection. So that's, when you have the a value on the outside, you basically multiply your y coordinates, the y portion of your coordinate, by the a value to get your new points. Or, like I said, make a table. Table always works as well. You can, when in doubt, you're graphing any function. I don't care how complicated that function is. If you know how to set up a table and get points, you can graph it. You can graph that function. So, SAT, assistance help, that's the thing to do. All right. So this is the change in the h value. Now, anybody remind me, what does the h value represent? What kind of shift? Good, horizontal shift. A negative means it's going to the right, a positive means it's going to the left, because it's always opposite of its sign. So we have our original function, and we're shifting each point how many units? Good, 3 units to which direction? Yeah. So horizontal to the right plus 3. So you're moving every point 3 units to the right. So we start with these points, and I'm moving them 3 units to the right. So 1, 2, 3. Same thing, 1, 2, 3. So it's going to look something like that. And then we sketch our graph. And before we move on, I want to talk about this in terms of geometry. Anybody know what kind of transformation this would be in geometry? What? I mean, it starts with it's translation. You guys remember translation? It's where you pick something up and just shift it. So all we did with this graph is we picked it up and we shifted it 3 units to the right. Before, we were doing more of what's called like a dilation for the first 2, and then a reflection for the last one. Last one's a reflection. First 2 were a dilation because we actually manipulated the shape of the graph in the first 2, right? The graph either got stretched or compressed. So it actually didn't, you guys remember isometry, rigid motion? It didn't maintain that in the first 2. But in the last one, this one, it did maintain isometry. It maintained its shape, okay? So that's just something to connect this back to geometry a little bit. So now that we did that one, let's try the next. This one is also a horizontal shift, but what kind of horizontal shift is this one? To the, yeah, the left, you're right. That one is every time, even, it's just, you have to think about it for a second. It's always the opposite of what you think it's going to do when it's horizontal. Horizontal shifts are, you know, opposite, just because how do I explain this? When you see a general equation in math that has a negative sign in it, that always means that the sign is going to flip when you do something. So that's just something to keep in mind. So this is the equation, y equals 2 to the x, and we're going to shift each one of these 2 units to the left. Just like this. So that's a horizontal shift, 2 units left. You don't have to write that. You can if you want to. It's up to you. It's your notes. But yeah, that's what the graph looks like. This is, again, another translation. Bad. The last 2 are what kind of shifts? Anyone know? Yeah, they're vertical shifts, right? And this time we're going, how many units, which direction? Down 4. Down 4. So this always tells you up, down, okay, when it's on the end like that. So we're going to go down 4 units. So 1, 2, 3, 4. And unlike with horizontal, vertical is straightforward. So if it's minus, it's down. If it's positive, it's up. 1, 2, 3, 4. And then 1, 2, 3, 4. So it's going to look something like this. Now, something important to note about horizontal shifts, vertical shifts that's unique to vertical shifts, is they change where your asymptote is. Because your k value changes, meaning your asymptote changes as well. On my original function, my asymptote was at y equals 0, but this one's at y equals -4. So your asymptote changes on vertical shifts. And this one's pretty straightforward. What are we going to do with each point? We're going to move it up 1. Good. So everything's going to move up 1 unit. And like I said, with geometry, this is like maintaining isometry. That's kind of the best analogy I can give you. The shape doesn't change, it's just shifted up. The first two types we did were not maintaining isometry because you changed the shape of the graph. And once again, our horizontal asymptote did change. When we do a vertical shift, it always changes. So do we have any questions about this part here? Alright, so we are going to try the next portion. So there's some important characteristics of exponential functions we need to talk about before we classify them, graph them, and all of that. So your horizontal asymptote is always in the form y equals k. It's always a horizontal line equal to whatever your k value is. You sometimes have an x-intercept. Depends on the graph. Some of them do, some of them do not. You always will have a y-intercept though, and you only have one of them, because if you had two, it wouldn't be a function, it wouldn't pass the vertical line test. That's a whole other story, right? And you can always evaluate it at x equals 0. This is such a key step, and so is this. These two steps right here are going to help you kind of get the bones of your graph to see what it's going to look like. That's kind of like to give you the general idea of what that graph's going to look like. Now, you can classify and know if it's going to be growth or decay based on your b value. So your b value is the one that has the exponent in it, okay? So you can do that by looking at its b value. And in this case, domains are always all real numbers. So the domain is always all real numbers for every exponential function, so you don't ever have to worry about figuring out the domain. And the range is determined by the sign of a and the value of k. So if for example, your a value is flipped, it's going to change the range a little bit. And the k value helps us determine where the asymptote is, where it's going off in one direction. So you'll see the easiest way to find the range is to actually just graph it and see the range, visibly see it, instead of trying to figure it out without looking at it. So let's go ahead and get started on this. So the classification, it's asking about growth or decay. So is this one growth or decay? You're going to look at your b value, which is the one that has the exponent on it. Is it bigger than 1 or between 0 and 1? Good, it's bigger than 1, so it is growth. It's growth because your b value is greater than 1, which it's 2, so 2 is greater than 1. Now your domain for any exponential function is always positive infinity, negative infinity to positive infinity, or all real numbers, same thing. Your asymptote is always, I'm going to go a little out of order, you're going to see. Your asymptote is always y equals what? K, which is what? 4. This number at the end right here. If it doesn't have one of those, it's 0. Range, we wait for the graph. X-intercept, you can find the x-intercept algebraically by plugging in 0 for y. However, if I plugged in 0 for y, you guys wouldn't know how to solve this yet, because we haven't learned how to solve where there's an exponent in the variable, a variable in the exponent, but we're going to learn that in the next few lessons. So you will learn how to do that, it's just not in our skill set yet. So to find the x-intercept, we're just going to look at the graph and find it that way by estimation. Now the y-intercept, you do have the skill set to find. So to find the y-intercept, you're going to evaluate x equals 0. So you're going to take your equation, and you're going to plug in 0 for x. When I do that, I'm left with y equals negative 4 times 2 to the negative 2 plus 4. Now, this is where a calculator is really helpful if you're not like great with exponent rules, which we did learn a few units ago. Anybody know what happens when you have a negative exponent? You bring it to the bottom, the denominator, right? So it becomes negative 4 times 1 over 2 to the second, and it makes it positive. Do you guys remember that with exponents? To make an exponent positive, you bring it to the denominator. But if you're really still not too good with that, you can just use the calculator. 2 to the negative 2 power is going to give you 0.25, which is what this is, 1/4, times negative 4 plus 4. I just did all that math in the calculator, and it gives me 3. So my y-intercept is 0, 3. So you can do that by just plugging in 0 for x and computing it in the calculator. Now, for the sake of time in this lesson, I'm not going to, and for space, on your sake, so you have a small little spot here, I'm not going to be computing every value in the table, like by hand. I'm just going to use the calculator and tell you what it comes out to be, and I expect you can do the same. I don't expect you to show me the work for each one. So, once you find your y-intercept, that's going to be around the middle of your table. So I'm going to put it in right here. You have 4 values. Put it somewhere in the middle of your table. That's one of the values. Now from here, this helps us determine what other values we would want to have in our table. Now, when you have a growth value and your a value is greater than 1, the absolute value of it, if your a value is really big, like in terms of negative or positive, big number, you want to pick values like 1 and 2 to plug in here. And then I'm also going to do negative 1. And I'll help you as we go through how to determine what values to put in your table. But this is where Desmos is really useful as well. Now, to get the answers for y, you would have to plug these values in for x just like we just did with 0. But I'm just going to tell you the answers to save us the time. So this is 3.5. This comes out to be 2, and this comes out to be 0. So you would get that by plugging in these x values into the function with your calculator, and that's how you would obtain those. Now once you have all of these, you're going to graph them. So negative 1 and positive 3.5 is 1, 2, 3, and then halfway up. 0, 3, 1, wait, I did that one wrong. So yeah, this one was good. 3.5, and then this one's at 3. This one's at 2. And this one's at 0. It's like that. So you can kind of see what it looks like, but you're not going to want to graph it yet. The next thing you're going to want to graph is your horizontal asymptote. So your horizontal asymptote is at y equals 4, so it looks like this. So that is your horizontal asymptote. And the reason that we always want to graph this is because it helps us kind of see what's happening with our graph. Because remember, your function's always bending away from the asymptote, okay? It's kind of like, you know, avoiding that. You can't actually hit the line. You can get really close to it, but you're never going to actually hit it. So it's kind of going to sit along the line. Like, you guys know that thing where it's like that joke, like, I'm not actually touching you, and they're like right there. It's like that, like with the asymptote. It's like sitting right there, but it's not actually going to touch it. Gets really close, really, really close, like literally like decimals away. For eternity, it gets decimals closer for eternity, but never actually touches it. So that's what your graph looks like. Now, once you've identified your graph, you can kind of go back and find the other things that we were missing. So what would be our x-intercept? Where do we hit the x-axis? Yeah, 2, 0, exactly. And this one happens to be exact, but there are a few that you're going to have to estimate here. Now, your end behavior is what's happening to your graph. And you're going to look at what's happening to your graph as your x value is going to negative infinity and as your x value is going to positive infinity. So what that means is basically on the left and on the right, what's your graph doing? So on the right here, as the graph goes to positive infinity, what's happening to my function? It's going down to forever, so it's going to negative infinity, right? So on that side, it's going to negative infinity. So as my function values, x values go up, my function's going down. Now on the other side, however, as my x values go to negative infinity this way, is this function going off to positive infinity? No, because it's never going to cross this line, is it? So it can't go up to positive infinity. It's actually approaching what value? 4. So one side of your end behavior always, with an exponential function, one side of your end behavior, depending on which way it's facing, will always be your asymptote. Okay? One side of this end behavior will always be the asymptote. It depends on how the graph is positioned, which one's going to be, but one of them will always be the asymptote. So you're going to have one going off to either negative positive infinity, and one of them going off to the asymptote, depending on the side. Now, is this graph increasing or decreasing? Good, it's decreased, going down. And then the last thing we're going to talk about is the range. So the range of this graph. Well, this graph range is up and down, all the y values this graph will take on. Now, since it's starting down, it's coming up from negative infinity, but it doesn't go up to positive infinity, does it? It stops at what y value? 4. And 4 is actually not included in the range. Why is it not included in the range? Exactly. It doesn't actually touch that line. It just gets really close to it. So we don't include it in the range. So let's try example 2, and then we'll take a break and finish after lunch. So this one we'll do, and then we'll finish up after lunch. So the next one we're going to look at is below. It is 2 as your a value, 1/2 as your b. So the easiest thing to identify here is this one, exponential growth or decay. Is your b value between 0 and 1, or is it greater than 1? Decay. So your b value helps you determine the decay. It's the only thing that will determine the decay, because it's 1/2. Okay. Now your asymptote is y equals -5. Good. It's your k value. Your domain, like all other exponential functions, is negative infinity to positive infinity. And the only other thing that you can find before graphing is the y-intercept, which is really important to graphing this. So to find the y-intercept, we're going to take our function, and we're going to plug in what for x? 0. Now, I'm just going to do the math and tell you what it is, because we don't, you guys know how to do algebra. So this comes out to be -4. This one you can kind of do in your head. 0 minus, it's negative, and it flips it, and yeah, it's -4. It's a plus sign, yeah, there's a plus. So your y-intercept is 0, -4. And this is going to help you determine where you want to have the kind of the middle of your graph. So let's say we'll do the middle right here at 0, -4. So around the middle is your y-intercept. Doesn't have to be exact. You can pick, you could have put it above and you still get the same graph. So when your b value is small like this and your a value is also small, so if it's decay and your b value is also, you're going to go negative instead. You're going to go -1, -2, and then we'll go 1. So that value in the middle kind of helps you determine which way to go. Now, you would, in theory, plug all of these back into the equation, just like we did with 0, but I'm just going to tell you the answers. It comes out to be -1, 3, and -4.5. So now we're going to graph all of that. So I'm going to zoom in to graph it. So that's at -2, -1 is down here, -1, -3, 0, -4, and 1, -4.5. Somewhere like around there, between the two. Now you're going to graph your asymptote. So what's our asymptote going to be here? -5. And then we can connect our graph based on the asymptote that we just found. Looks like that. That one actually I drew pretty decent compared to the other one. So now we're going to go back and fill in the missing blanks that we had. So our x-intercept, in this case, this is a prime example of estimating it. So see how we have an x-intercept right there? Anybody want to give me an estimation of what they think that might be about? Approximately? -2.5. Good, -2.5. That's a good estimation. And let's determine our end behavior. As x, we always go x goes to negative infinity, x goes to positive infinity. So in the negative infinity direction, on the left side of my graph, which way is my function going? It's going up forever, so it's going to positive infinity. And on the other side, as it goes to the right, what's happening to my graph? It's approaching what? -5. Good. Is this graph increasing or decreasing? Decreasing. Remember, when you do increase, decrease, you always read it from left to right. So from left to right, if you were on a slide and you started up here, you're going down the slide, right? Not up the slide. Now, as for your range, you're going to look at the graph and determine what's the lowest y value that your function goes to. Yeah, and it doesn't actually touch -5, but it starts at -5. And then the highest it goes is positive infinity. So, any questions about that? So after lunch, we're going to do a few application problems, and then you guys will have about 20 minutes for your assignment.